about 11 o'clock on the dot. Welcome, everybody, and thank you for joining us for the EnSafe 2023 Client Education Series webinars. My name is Rich Heinzenberger. I'm a project manager here at EnSafe, and today's presentation is on hazardous working environments in the aerospace industry, and it's being presented by Cody Ushak, who is out of the EnSafe Dallas, Texas office, and Cody is a senior project manager with EnSafe. I would like to remind you all that if you have any questions, we'll try to get to those toward the end of our presentation today. But again, welcome. Thank you for joining us. And I will turn it over to you, Cody.
All right. I appreciate the introduction, Rich. Good morning, everybody. It's early for some on the West Coast. I'm in Central Time, so 10 a.m., not too bad here, but we appreciate everybody joining us. This is a presentation that it should be exciting. I have a penchant for delivering presentations on specific working environments, so hopefully you'll enjoy it. Well, hello once again, everybody. My name is Cody Ushak, as Rich had mentioned, certified as a CIH, CSP, CHMM. Got about 10 plus years of experience in general industry specific to aerospace, worked in research and development and big technology sectors, have experience in general consulting, compliance, project management, program management, and a slew of other things. But I would say my areas of expertise definitely include industrial hygiene. That's my MO. That's what I love. That's what I try to do as much as I can. Environmental remediation and sustainability, certain elements of air pollution control, radiation control, public health, as well as safety management systems and ISO lead auditing, as well as general compliance auditing. So once again, thank you for joining us. So what we're going to go through essentially are various different hazardous operations that you can expect to encounter in the aerospace industry. This is going to be particular to mainly chemical exposures, but we'll also talk about flammable environments, certain explosive environments. But I do want to say this is not all inclusive of everything you may encounter in aerospace. That's fairly obvious, I would think. We've got an hour here, so the goal is to teach you as many cool things as we can. So one process that you will definitely expect to encounter in aerospace is sandblasting, also known as abrasive blasting. It's often utilized to shape, form, or roughen surfaces and remove contaminants from particulates. So you want a clean final product, and sandblasting is a common method of application to get there. So another thing that you may expect to see abrasive blasting used for is removing surface coatings from different metals if parts need to be reworked or if there's errors or quality defects. It's just a common operation, also a high hazard operation. There's different blast media. The one that kind of draws the most ire, in my opinion, is blast media that contains respirable crystalline silica. That's a very, as everybody knows who's familiar with industrial hygiene, as well as OSHA compliance, you have your silica standards. So there's very specific regulations to abide by when silica is involved. So as far as the different hazards that are generated, in addition to that, you may expect to see toxic metal particulates if you are blasting certain coatings off. Aerospace coatings are very commonly known to contain lead, cadmium, hexavalent chromium. Certain blasting booths can also be extremely noisy. Ideally, when you're performing these types of operations, you're going to want to perform them within a glove box, such as the one on the bottom right of the screen. That's if the part can fit in a glove box. Oftentimes, if parts are large, you may need to wheel them into an actual blasting booth. And obviously, blasting booths contain a high level of hazard when you think about noise, potential exposures, flying particulates. So with that said, there are some recommended controls to contain and limit hazards in the workplace while performing these operations. So as we go through the hierarchy of controls, obviously elimination and substitution should be considered. So the use of a less toxic blasting media may be something you want to take a look at. I mentioned earlier, respirable crystalline silica is a major hazard associated with this type of operation. So maybe considering the use of a non-silica based blast media. If you go to the process portion of the slide, there's just a few other examples of potential blast media you can use that may not contain silica. So if this is something you encounter on a day-to-day basis, challenge your workers, challenge your leaders. Hey, is this what we need to do? Do we need to do blasting with silica-based media? As mentioned earlier, blast cabinets are always a good option. They fully contain the hazard, still a little bit of noise associated with them, but at the end of the day, much safer operation than performing a large-scale operation in a massive blast booth. Always isolate these operations from other workers and from other workers as well as other operations within the facility. One problem with these things is that leaks are well known to be prevalent. If maintenance isn't paramount in your operation and these things start leaking, you're going to expose people outside of the operation, and you don't really want to do that. You want to minimize exposures to the greatest extent possible, and personnel as well. Minimal personnel around these operations. That's critical in reducing risk at your facility. So equipping blast rooms with localized exhaust ventilation is also a must if you are performing these operations within a blast booth. And finally, if respiratory protection is indeed required, you would probably be best served to utilize what they call a Type CE NIOSH certified airline respirator with a blast helmet. So that protects you from exposures, protects you from flying particulates, and it's actually a certified via NIOSH style respirator now. So there's more information on that. I'm not going to present a lot on that specific respirator today, but if you have any questions about that in the future or right after this, feel free to contact me. I'm going to leave my contact information at the end of this presentation. So another common hazard is etching, pickling, passivation using acid dip tanks. Essentially, these processes are meant to clean, engrave, or treat various metal surfaces. They're typically using strong acids to do so. So just to dive in a little bit deeper on the specific types of dip tank processes, etching is essentially engraving, mainly performed on aluminum, copper, and titanium surfaces. Pickling is used to clean and treat, also used on aluminum, copper, and titanium surfaces. And passivation is a method to treat or clean stainless steel. So essentially, the end goal of these processes is to prevent rust. These are all corrosion-resistant coatings that are applied, and it is a high-hazard environment, as you can imagine, and we'll explain why shortly. One note on this too, these dip tanks and these types of processes often require the use of a reducing agent for copper plating and electrolysis baths specifically. Formaldehyde is a common ingredient used in these reducing agents, as is methanol, monoethanol amine, I should say. So in addition to these strong acids and the potential application of hexavalent chromium-based products, you're also dealing with some acutely toxic materials as well, as you can see here. So specifically, as far as hazards that may be generated go, airborne acid mists, of course, if your dip tanks are heated, if they're aerated, you can expect to see things like hydrochloric acid, sulfuric acid, nitric acid, any strong acid. HF is something that people like to mess around with, mainly in research and development to try to better their processes. But HF has with it a very high hazard level when it comes to exposures in the workplace. So just be very cautious if you're using hydrofluoric acid. Additionally, you can expect to see certain toxic gases in the process if they aren't controlled properly, such as chlorine, phosphine, fluorine, and some of those other to the right of the periodic table type gases, we should say. So passivation of stainless steel also may generate nitrogen oxides if nitric acid is used. And as I mentioned earlier, hexavalent chromium can be a prominent hazard if trivalent chromium oxidizes or forms during the processes. If something like chromium oxide is utilized or chromic acid is utilized in this process. So the ACGIH Industrial Ventilation Manual does have specific ventilation callouts to reduce risk in the workplace and to provide the proper ventilation. So as you'll go through these slides, you're going to note on the bottom of some of the sections, you're going to see something called a design standard. That's simply for your reference. We're not going to go through all of them, but if you wanted to highlight them, you could always go back and reference the ACGIH Industrial Ventilation Manual. I unfortunately only have the 29th edition handy. However, there are updated versions. I believe the 30th is definitely out and the 31st may be coming soon, but generally it'll put you in the right ballpark. So as far as recommended controls or required controls to help assist with reducing risk from these processes, one thing that should always be considered, if feasible, is closing and capping your dip tanks. Just because they're aerated, they may generate acid mist and things like that. So if you're able to feasibly close or cap your tanks, definitely do so. It's common practice to negatively pressurize these rooms and separate them from other processes due to the high level of hazard contained within. Always wearing the appropriate PPE, corrosion-resistant aprons, corrosion-resistant gauntlets, and things like that. Reviewing the safety data sheets for the products you're using. That'll tell you all of the relevant hazards associated with the processes. But it's good to know these things as well on your own, because if you're performing a qualitative exposure assessment or outlining an industrial hygiene sampling plan, these are some things that you're going to want to add. You know, what controls are present, what PPE is present, what are we doing to minimize risk and control risk. So additionally, in these types of operations, you're going to see slotted ventilation systems. If you look on the picture to the bottom right and you look in the rear of the tanks, you see those slots. They require a significant amount of airflow to control mists at the generation point. So the design standard, as I mentioned earlier, you could find it in the ACGIH Industrial Ventilation Manual. However, it's good to talk to your A&E firms if you're starting up one of these systems or you're rebuilding one of these ventilation systems, just to make sure you're getting that cross-sectional airflow that's going to contain and capture mists and fumes or whatever types of hazards are generated from these processes. So CNC machining, as you can imagine, is quite prominent in aerospace and many other industries. It's pretty much the backbone to how parts are made. For those unfamiliar, CNC stands for computer numerical control. More or less, you input codes into one of these systems, and then you essentially watch what goes on. They shape parts. You don't have to do much hands-on work, just making sure that your controls are set properly. So it's a pre-programmed computer software dictating the movement of factory tools and machinery. Common CNC machines that you will see and encounter: lathes, grinders, mills, routers, drill presses. There's an abundance of different equipment, and these are some awesome apparatuses if you've never had the opportunity to check out something like a Mazak, which is a very common CNC tool used in various different industries. So one thing about this, you could machine various different types of metal. So commonly, as you can imagine, aluminum and stainless steel are used all over the place. Titanium is a common metal that's used. And I've often, or I should say not often, but I've also seen manganese machined from time to time. Not necessarily in aerospace, but I do want to talk about it a little bit just to discuss the hazard associated with manganese. So coolant is utilized in these processes as well, basically used to remove heat from the workpiece as well as the cutting tool, and it prevents the tools from exceeding critical temperature ranges. So if you exceed critical temperature ranges, you're going to have fire hazards. You're also going to promote poor use of the tool. Tools could break at heated temperatures. So nothing good comes out of overheating your tools while performing machining processes. So as it relates to hazards, in particular, coolant mist is probably the big one as it were, associated with this type of process. The coolant gets aerosolized, in particular if it's not captured at the source. Most machines, when you're doing your design review up front, you're going to want to install some sort of local exhaust ventilation or scrubber system to trap coolant and contain coolant, but often that gets overlooked. Most aerospace industries I've been in, whether I've worked in one or did consulting work in one, they do a very good job of controlling mists from the coolant. However, I've also been in, some startups and mom and pop shops where it's not necessarily something that's considered in the design review, whether they don't have money for it or they don't have the intellect to understand the hazards associated with coolant. But always when you have the opportunity, think about controls in the beginning of the process. So with that said, in addition to coolant mist being an inhalation hazard, they're also very prone to giving employees skin contact dermatitis, skin redness, itching, swelling. I've been around people who have had exposures to coolant on their skin, and that has happened. They have a sensitization to it and develop some sort of skin contact dermatitis. So you want to prevent that as best you can in the workplace. Another thing that you may have to deal with coolant in particular is bacterial growth. It's very important to make sure that you're either treating your coolant to prevent bacterial growth, or you are removing it from the bottom of your systems. Once it's used, some people will let it just kind of sit there under the machines and not pump it out. It's very important to either treat it and or pump it out routinely and regularly. If you've never experienced the stench that is bacterial growth in coolant, I absolutely don't recommend it. You could smell it throughout the entire facility. It's pretty gross. People don't like it. People complain about it, reasonably so. Just something to consider. Treating the coolant. There's different biocides that can be added to coolant to help prevent bacterial growth. So we mentioned some of the recommended controls a little bit earlier. Obviously, local exhaust ventilation system is a recommended control for containing any type of airborne hazard. Nitrile gloves when touching parts with coolant on them. Mentioned earlier, adding biocides or microbicides to the coolant mixtures to prevent bacterial growth. And finally, maintaining an adequate PM schedule as it relates to pumping out and cleaning your coolant sumps underneath some of these machines where coolant does collect during the process. My personal favorite, spray coating and powder coating. Essentially, the process is using paint and primer, forcing it into the atmosphere under pressure onto parts and surfaces to provide a coating, whether it's for corrosion protection, aesthetics, doesn't necessarily matter. The hazards will be fairly similar depending on the ingredients of your spray paint. So when spray coating occurs, the liquid breaks up to form a fine mist via atomization, and there's several different types of spray systems. The one that I'm most familiar with is high volume, low pressure, but there's airless spraying options, low volume, low pressure, gravity feed, as well as compressed air. So there's many different hazards associated with this type of operation. The paint components are variable. So you're going to have a pigment, a binder, the liquid itself, and different additives possibly for the paint components. So there's a wide range of volatile organic compounds that may be present in the solvents. Corrosion-resistant coatings may contain chromate compounds. So anything that may have zinc chromate in it, strontium chromate, various different types of pigments, you have to be wary of hexavalent chromium exposures and make sure you're evaluating that. And one thing to note, when you read a safety data sheet, typically it will not say in the ingredients hexavalent chromium because the material isn't in its neutral state when it's being applied hexavalent chromium per se. When it's airborne and through the process of atomization and oxidation and all that fun stuff, whatever it may be, hexavalent chromium will be an end contaminant at the end of the day. So if you're applying polyurethane coatings, there's going to be potential isocyanate exposures associated with that. There's going to be coloring agents in the pigments such as carbon black and talc, acrylic material in the binders, and some biocide material. They'll throw in something like formaldehyde. So just important to understand the ingredients involved with your process. Talk to your painters. What are you doing? What paints are you using? Check out your safety data sheets. And most importantly, make sure you're doing and outlining a very thorough qualitative exposure assessment to make sure you're capturing all of these different target analytes. So controls for these type of operations are usually involving open-faced or fully enclosed spray booths and mixing booths, need adequate face and cross-sectional velocity, and also ensure you're doing routine filter changeout schedules. If you're not, it's going to impact the efficacy of your system. And there's also OSHA-specific and NFPA-specific requirements for designing and installing spray booths. When you're working in a booth and spraying paint all over the place, regardless of your ventilation, you're going to, of course, want to obtain relevant and accurate occupational exposure information and data. But half-face respirators are usually the go-to during spray booth or spray painting operations. Wearing nitrile gloves and as well as a Tyvek suit to protect your skin and body is paramount as well. In relation to spray coating, the curing process usually occurs very soon afterwards. So during the curing process, the solvent dissipates and evaporates. It gets removed from the pigment, which is the color that ultimately your paint results in. The paint layer hardens and becomes durable. So that's the end goal of the curing process. Sometimes hardeners or catalysts are mixed with the paint to accelerate the process. Heating material will also accelerate the curing time, and heating will occur in dedicated ovens that are often exhausted to the exterior of the facility. One note on heating: if you heat certain chemicals to decomposition temperatures, you're going to have off gases and things like that. So it's really important to understand what your set cure temperature is. It's also important to understand potential thermal decomposition products that may occur at certain temperatures. So oftentimes your safety data sheets, if you looked at, the reactivity and the compatibility and the thermal decomposition section, that will all be outlined. But sometimes you have to think with the mind, in the chemistry world, and just try to take your best guess at evaluating what off gases may be present. So in addition to thermal decomposition products, you're obviously going to have volatile organic compounds. They're going to evaporate. That's part of the goal of the curing process. So as they evaporate, the VOCs are going to be moving through the air if they're not collected locally through an exhaust system. And if vapors are heavier than air, which oftentimes solvent vapors are not, they can accumulate in low-lying areas, presenting a potential explosion hazard. So very important to always utilize local exhaust ventilation where feasible to capture contaminants at the source. So we mentioned using local exhaust ventilation, the operations being vented to the building exterior. Curing often occurs in paint booths. People will just do their paint activities. Certain paint booths have controls where you could elevate the temperature, but that's not a bad bet when you're performing these operations from a simplicity standpoint. You perform your painting activities, you leave your equipment inside until the cure time is ready, and you take it out. It's already controlled, but some people don't have the capacity to do that. If your throughput is too much, you're not going to be able to leave parts in there. So with that said, evaluate what you can do with your team. What's feasible? Are we doing the right thing? Are we minimizing risk? And at the end of the day, it's a collaborative effort between multiple teams. So abrasive activities, in particular, grinding, sanding, polishing, and deburring. Grinding is simply a subset of cutting, multi-point metal cutting processes. Sanding and polishing are performed to smooth and flatten surfaces or remove coatings. And deburring is shaping and smoothing rough ridges or edges. Most of these processes will involve the use of flat discs or wheels to contact various surface metals. And once again, similar to the abrasive sandblasting slide, the hazards are going to be fairly similar. When you're performing this type of work on straight, metal or stainless steel alloys or anything like that, there's going to be the production of very fine metal dust particulates, which can be toxic. If manganese is fairly toxic, nickel, hexavalent chromium shouldn't really have hexavalent chromium, but if you're sanding or grinding off or deburring hexavalent chromium coatings to rework a part per se, it may be a hazard. But the straight metal for stainless steel in the alloy will be metallic chromium. So you shouldn't have hexavalent chromium issues unless you are sanding or grinding or polishing a coating that actually contains hexavalent chromium. It's a common misconception. People get hell-bent on evaluating hexavalent chromium in the welding industry, and then they just think, oh, well, now we have particulates in the air from doing this type of work. But the reality is welding generates hexavalent chromium when you're doing these activities on straight, pure stainless steel alloys. That's not going to be the case. So keep that in mind. But we also just talked about other heavy metals. Chromium's not your only concern. Certain coatings may contain lead, they may contain cadmium, nickel, manganese. But just evaluate your process. Are we performing these activities on pure metal? Are there coatings or sealants or anything that we're sanding or grinding or polishing off? for ease of operation. It's just important to understand your process to properly evaluate what hazards are actually present. So from a control standpoint, downdraft tables are usually the go-to when working smaller parts. They usually do a fairly good job of containing these type of activities, but push-pull systems and wet systems are the most efficient. What I mean by a push-pull system is a capture system that physically pulls air down while pushing air down. So it expands your capture zone. When you're doing these activities, you can imagine, for example, if you're sanding on a surface, those particulates that you're sanding off, or particulates that come off during the process, are going to have a high transport velocity. So with a high transport velocity, you're going to need a high capture velocity to make sure those particulates are captured during this process. So for larger operations, for example, the removal of surface coatings on large parts, sanding and dust boots are often designed, installed, and controlled. They're not cheap to build, they're not cheap to maintain. So it's really contingent upon exposure data. Are your downdraft tables doing enough? Are you minimizing exposures to the greatest extent possible? And second to that, how large is your operation? We may not be able to fit it in a typical downdraft table. So in addition to those controls, luckily, Clayton and other vendors, not to shout anybody out or promote favoritism, but I know Clayton quite well and have used Clayton. They will actually have vacuum shroud attachments with HEPA filters that you can attach to these discs. So if you see that grind or the sanding disc in the bottom right corner, the reason for those holes is that air moves through that. It's capturing, I should say it's moving air away from where you're generating it into your vacuum. So it's not 100% effective, but it helps a lot, and it's cheap, and they don't really get in the way as much as you think they would. So at the end of the day, these type of processes always need local exhaust ventilation. You could never just perform sanding and polishing out in the open. You're going to create a mess. You're going to have exposure hazards. You're going to have combustibility hazards. Most of these dusts are going to be combustible at certain in certain areas. So just something you need to evaluate. Perform a dust hazard assessment if you need to. Make sure you're identifying potential contaminants while performing your qualitative exposure assessments. But this one in particular, I pretty much said we're going to focus on airborne particulates and airborne hazards, but flammability and combustibility is a big deal when it relates to these processes in particular. So vehicle testing, and this could be testing of vehicles for maintenance operations or testing of vehicles that are being built or being provided to a customer, but they do have to get tested indoors at times. And when that's occurring, it could be part of operational testing, could be part of a power transfer test. And there's different vehicles that you will see in the aerospace industry that this testing is performed on, including tanks, including launchers, different ground vehicles, and even your standard diesel trucks that may be part of your facility's fleet. So with that in mind, there's a slew of different hazards generated from the combustion or incomplete combustion process, including carbon monoxide, potential for generation of nitrogen oxide, sulfur dioxide, diesel particulate matter, which you could sample for directly, thankfully, different hydrocarbons, alcohols, aldehydes, and ketones, most of which cause skin, eye, respiratory tract irritation. Some of those listed elements are acutely toxic. And some of them are carcinogens. So it's very important to evaluate your exposures. Take a conservative approach as well. You really don't know what specific hydrocarbons or alcohols or aldehydes may be generated during these processes. So performing profiles, an aldehyde profile, a VOC profile, a TO15 sample if you need to. But at the end of the day, if you're not controlling these operations, by that, I mean your exhaust system in particular, you're going to have some degree of hazard associated and some degree of exposure associated with these activities. Thankfully, the ACGIH Industrial Ventilation Manual has a specific call out on these operations and this activity. So they will tell you what the required CFM is of your exhaust system based off of your rev numbers, what are your RPMs, what is your temperature, and a couple other things. And temperature, I mean your exhaust temperature. So it's all outlined. If you ever need to evaluate this, it tells you all of the different variables to consider in the ACGIH Industrial Ventilation Manual. So exhaust snorkels are usually the go-to that directly attach to the exhaust system and exhaust to the exterior of the building. And an additional control to consider are direct read instruments for things like carbon monoxide. Carbon monoxide, as it relates to incomplete combustion for diesel, it may not be something that's too prevalent, but generally, if there's going to be incomplete combustion and you're going to have other hazards present, there's a good chance that carbon monoxide is present as well. So it's a good indicator and a good precursor if there are exposure concerns or IDLH conditions in the working environment. So this is not just specific to aerospace. Nanoparticulates and nanomaterials are becoming a fad all over the place, especially in technology. But anyway, nanoparticulate is defined as a very fine particulate with a cut diameter of 1 to 100 nanometers. So that's obviously not something you could see visibly without a microscope or anything like that. So when you have nanoparticulate exposures, it's not something that you're going to be able to visually see like some other exposures like dust and particulates. So it's something that you'll just have to know when to evaluate that. So a few common activities and operations where nanoparticulates may be something to consider include fabrication of 3D printed circuit boards and additive manufacturing. There's a large range of different materials as well. So aluminum, different metals, copper, pretty much anything. You could involve additive manufacturing is kind of neat, but you could utilize several different sources. They have higher printing resolutions, which is why at the nanoscale, these materials are most effective. And also 3D printing and laser cutting. Once again, usually large 3D printing and laser cutting systems are fully enclosed. However, people are pumping out 3D printing systems like wildfire lately, and just there's new ones hitting the market all the time. And intrinsic controls aren't something that manufacturers are always thinking about or caring about. So if you've got anything going on that may be producing nanoparticulates, definitely want to evaluate potential exposures, evaluate recommended controls. But one thing in particular for nanoparticulates, they've got high reactivity due to their cut diameter, and there's various routes of exposure. So inhalation, obviously, the particulates are fine. They're going to go through your entire respiratory system because they're going to be respirable, inhalable, thoracic, all of the above. Ingestion is a problem because you can't see them. So if particulates are getting collected on different surfaces, or if you're working in a lab and you bring food and drink in there and you don't identify dust as a problem because you can't see it, these types of materials can collect in your food, in your drink, and ultimately can become an ingestion hazard. And because of their small cut diameter, they could very, very easily enter through the body via skin contact as well. So several different routes of exposure that are realistic associated with nanomaterials. So it's very important to keep a very clean working environment, maintaining great housekeeping, very critical in minimizing exposures. So additionally, many nanomaterials are comprised of metals, many of which are carcinogens, and they also will give you some sort of skin contact irritation, eye irritation if exposure to the eye occurs, or respiratory tract irritation. So beyond them being nanomaterials, they also may be carcinogenic or toxic. So it's important to understand the chemistry of the materials your teams are working with. As far as controls go, skin protection is a must. You definitely want to protect your skin, as we mentioned earlier, due to nanomaterials' ability to quickly navigate through your skin into your body. Performing these activities in fume hoods with negative pressure, there's actually a common thing now in research laboratories and college chemistry labs. A lot of folks are implementing nanomaterials programs where they're outlining proper face velocity for their fume hoods, making sure that these type of processes are controlled as well as possible at the source. As we said earlier, you want to develop closed ventilation systems when you're printing or performing some sort of additive manufacturing at a larger scale. And respiratory protection is often required. And what type of respiratory protection is contingent upon your occupational exposure data. One thing about nanomaterials, it's kind of unique to sample for them. I know SGS Galson is working with, I want to say, AIHA right now to determine the appropriate sampling methodology for nanoparticulates, but there's not really a safe level established of general nanoparticulates. There's titanium dioxide, I'm pretty sure, has a specific exposure limit for nanoparticulates, but as far as general nanoparticulates goes, I'm not familiar with any sort of exposure criteria. So it's important to do your research in terms of what are available standards or what are available scientific opinions on safe levels of nanoparticulate exposure. So soldering is essentially just using a metal alloy to make strong permanent bonds to connect or attach different parts together. There's various types of soldering activities, simple hand soldering, which a lot of us, if we were in engineering or some sort of chemistry background, you may have done this type of activity in a college setting. Selective soldering is soldering that's got a higher degree of hazard, produces much more fumes than some of these other soldering activities. But wave soldering and pot soldering, they're common types of soldering that you'll see in aerospace and other industries. So with that said, the soldering often is associated with the use of a rosin flux material, which is used to remove metal oxides during the joining process. And the thing with rosin flux fumes, they're not necessarily highly toxic, but they are sensitizers. If you see fumes during the soldering process, they are mostly going to be comprised of these rosin flux materials, which can produce occupational asthma in the worker, eye, skin, respiratory tract irritation. Another issue with soldering, of course, it's a hot activity. Burns are prevalent for employees who aren't protecting themselves properly. In addition, solder wire and solder braid often contains lead, can contain other toxic metal alloys as well. So something you'll have to evaluate during your soldering activities. People tend to get a little bit overzealous with getting worried about lead during soldering activities. Your main concern with lead for hand soldering in particular at a solder station is surface contamination. You'll notice that in the fumes, people will just automatically think, oh, we've got fumes, we're soldering using 6337 lead tin wire. We're going to go crazy sampling for lead. It's a great thing to do. You want to do that. You want to maintain exposure data, but at the end of the day, the majority of what's in that, the fumes associated with soldering is going to be from the rosin flux or the flux. So not saying ignore lead, but evaluate the situation appropriately. Lead has an extremely high melting and boiling point. Keep that in mind. Soldering is likely not to reach those temperatures. However, as I mentioned earlier, surface contamination is a problem. People are handling these solder wires and the braid at their workstations. So there's going to be residual contact, or I should say there's going to be residue from surface contact from the straight solder braid and the solder wire. So controls, it really depends on your operations. Ideally, for hand soldering, you're going to want to use a local smoke eater. They're cheap, they work fairly well, and it's a best practice whether you're trying to reduce exposures below PELs or occupational exposure limits, or you're just reducing irritants in the fumes or whatnot. It's a great practice to utilize any sort of mobile fume extractor. They're usually $100 for some of them, so it's usually a good idea. It's not too cost prohibitive. So with that said, for your larger scale soldering activities, wave soldering, selective soldering, pot soldering, localized exhaust ventilation systems are very important, making sure that they are designed properly for what you're doing. there's usually some funky designs because selective and wave solder machines are so unique. So evaluate that. I know I've been in many facilities where they've had ineffective local exhaust ventilation systems associated with wave and selective soldering, just because there was bends and curves all over the place within the ventilation system, which was greatly reducing the efficacy. So it's important to map this out in the design phase. But if it gets to the point where you're evaluating controls after the fact, take a look at what you're able to do and provide the most efficient means possible of controlling emissions. So we mentioned surface contamination a little bit earlier. Very important housekeeping in areas where soldering is a common activity. Frequent cleaning. You want to clean daily, not at a minimum, but try to make it part of your daily standard operating procedure, cleaning your workstations, cleaning your workbenches. Because as I said, that lead, the sources of lead, they could add up. If you do your surface testing, you could get very, very high levels of lead if you're not keeping up with your housekeeping. So keep that in mind. It's always great to establish a solid housekeeping protocol. So welding, which is a very common activity in all industries, not just aerospace, but happens to be extremely common in aerospace due to the activities that are performed to make product. But in short, welding is just uniting or a union of metal pieces by heat or compression. There's usually a shielding gas associated with the welding activities. So shielding gases are typically going to be inert gases, things like nitrogen, argon. Some people use helium, although most welders I know don't prefer that. Not at all times, but commonly a flux is also used to prevent the filler or melted metals from becoming contaminated or oxidized. But the shield gas and or the flux can be used in tandem to prevent that from happening. So the three most common types, I should say the four most common types of welding activities include MIG and TIG welding, which are also known as gas metal arc welding and gas tungsten arc welding, stick welding, also called shielded metal arc welding, and finally plasma arc welding or flux board arc welding. And depending on what type of weld that is being performed by your workers, there's going to be different types of hazards associated and generated with each. So the most obvious hazard from these processes is going to be the generation of metal fumes. However, as I mentioned earlier, that's contingent upon the type of weld. So TIG is known to create less fumes. MIG has quite a bit more fume generated. Stick welding, plasma arc welding also generate a good deal of fumes. So keep that in mind when you're trying to understand your processes and developing your qualitative exposure assessment or sampling plan. Talk to your workers, get a better understanding of what they're doing. What type of weld are you doing? How often are you doing it? Are you concerned about exposures in the workplace? Do we need to help you control them? So in addition, when you're welding on stainless or carbon steel, you're going to have metal alloys within those chemistries of that metal. So hexavalent chromium, nickel, cobalt, and manganese are common constituents in those fumes when you're working on stainless and carbon steel parts. Additionally, if you're using flux and shielding gases, ozone, fluorine, carbon monoxide, and nitrogen oxides, they may be generated gases as well. Often forgotten about commonly when you're performing a qualitative or developing a qualitative exposure assessment and you're outlining potential hazards in welding, you may overlook these gases. I've seen overexposures to ozone. I've seen almost IDLH conditions for carbon monoxide during these processes where somebody was welding in a confined area. So don't overlook this. If you're unsure, it doesn't hurt to sample for these. Nothing here is very expensive when it comes to cost versus company value. But the most important thing is make sure you are doing a thorough risk assessment, making sure you're capturing all potential exposure scenarios. In addition to straight contact on metal, rework is a common requirement in aerospace per client request or client contract requirements. with rework comes a great level of different hazards. There's paints, there's sealants, there's adhesives, at times even historical degreasers used on different types of product. And ideally, we talked earlier about removing them using abrasive blast or sanding, polishing operation or activities. However, you may not always be able to get to them. So, people may take shortcuts where they can't physically remove these materials and weld right over them. When you do that, there's going to be all sorts of thermal decomposition products. If you're working on degreasers, many of those thermal decomposition products may be toxic chlorinated compounds. So with that said, really think about what you're doing. This is where, if you are performing these activities on different types of paints, sealants, adhesives, degreasing components, you're going to have to put your chemistry brain on, because these are the type of things that may not be outlined in safety data sheets very thoroughly. These may be legacy chemicals that were applied 30 years ago that may no longer exist. So really take a look at what you're doing and look at things from a worst case scenario. And as always, if you need help with chemistry or anything like that, contact the appropriate people. Don't make assumptions, but it's very important not to overlook that. And additionally, of course, when you're using inert gases, there's potential for oxygen depletion in an oxygen deficient environment. So also evaluate that, making sure you have good dilution and general ventilation. If needed, forced air ventilation to make sure that oxygen depletion is not a problem in your work area. So controlling welding emissions is usually done by a welding snorkel system, an elephant trunk. They could be fixed to the building, they could be portable, but they should be placed as close to the operation as possible without impacting the weld integrity or the quality of the weld. So if you put a welding snorkel too close to where the weld occurs, you're going to suck up all of that inert gas, and it's going to lead to a poor weld. So evaluate that, talk to your welders, what's feasible, what can we do for you to be safe and to get your job done appropriately. Respiratory protection is commonly required during welding activities. There's half face, full face, supplied air respirators. I should say powered air purifying respirators, not supplied air, but PAPRs are what welders really like to use. They're cool, they're comfortable, and they're good at containing exposures and making sure the workers aren't exposed to hazardous elements. One thing I wanted to note too on the welding snorkel system, there's also design standards in the ACGIH Industrial Ventilation Manual. So if you ever want to take a look at that, I have it cited right there below. But typically, I've found that 6 to 12 inches, placing the exhaust inlet 6 to 12 inches, I should say, away from the capture zone or the point of where the weld is generated, that's usually the best bet from an efficacy standpoint. And finally, we'll talk briefly on hypergolics. In aerospace, you can imagine they utilize rockets and things like that, spaceships. So hypergolics are utilized to propel the rockets in the rocket motors. Hypergolics react spontaneously when in contact with an oxidizer to do so, but ultimately the constituents of hypergolics are extremely acutely toxic. So in particular, hydrazine, monomethylhydrazine, we'll call it hydrazine for short, dinitrogen tetroxide, those are the big two that you will see. People don't commonly use chlorine trifluoride in production, but it's a commonly used chemical in testing and research and development. And it is extremely reactive, basically explosive in contact with air, also known as the stupidly dangerous chemical. So if you're using chlorine trifluoride, you really want to evaluate your controls. But for the most part, it's not something that you will typically encounter in the workplace, but the possibility does exist. So as far as associated hazards go, there is obviously potential for oxygen deficient atmospheres because of the presence of high pressure gases and cryogenics, such as helium and nitrogen, that are utilized to support the hypergolic process. Talked about the high level of acute toxicity for hydrazine and dinitrogen tetroxide. Chlorine dioxide gas may be generated during the scrubber treatment process, so it's important to control that appropriately and evaluate that as a potential exposure scenario. If organic decomposition occurs, hydrogen sulfide gas may also form. And once again, if people are messing around in research and development world, they may decide, let's try out chlorine trifluoride, which, as mentioned earlier, is extremely reactive, can explode in contact with air, and it's also acutely toxic. So it's got the whole kit and caboodle from a safety and health hazard standpoint to worry about. Controlling these operations is not that easy, truthfully. If you were to have a spill or anything like that, it's most likely going to lead to an evacuation scenario. However, what you can do is identify if a spill occurs or identify the need to evacuate. So installing monitoring stations to continuously monitor for different acutely toxic materials used as hypergolics, such as hydrazine and dinitrogen tetroxide. They can be associated with the building management and building alarm system. So if they do pick up levels of one of these harmful chemicals at, percent X or X% or whatever, it'll automatically trigger the building alarm, identifying the need to evacuate the workplace. So in addition to that, portable detection systems as well. So the monitoring stations that are fixed obviously can be attached into the building alarm system and the building management system, but also having the ability to test direct read for these type of vapors in the air if there was a potential exposure scenario. With that said, you never want to put yourself into a harmful atmosphere. So be very cautious if your approach is going to be to utilize direct read instrumentation to evaluate potential exposures. In addition, because of the cryogenics and high pressure gases, making sure that oxygen sensors are located in relevant areas, always having an on-site HAZWOPER team and emergency response equipment. At worst, identifying a third party to handle these services for you, but making it a part of your emergency action plan, your emergency response plan. These things do happen. Incidents do occur. These are very harmful materials that you really do not want to be exposed to. So when you're working on parts, where feasible, smaller parts, you could utilize a sealed glove box in case there was a spill or anything like that. At least it would be controlled and exhausted. Additionally, for larger scale operations, performing these type of activities in a negative pressure environment. So if there were a spill, it's contained and you could always remove yourself from that environment. And if it truly is negative pressure, it should contain and capture anything as it relates to a spill. All right. Well, that is all I have for everybody. I know it was kind of a lot. I wanted to get as much information included as possible, so I apologize if it felt overwhelming, but I hope it was a good learning experience for everybody. It's one of my favorite things is, learning about specific hazardous working environments, whether it's in the aerospace industry, whether it's a foundry, whatever it may be. I do love this type of conversation, so I hope everybody was able to at least take away something or learn something. And it's been my pleasure talking with you all, and I appreciate your time. But if anybody has any questions, please let us know.
Great job, Cody. I would just recommend or remind everybody that all of these webinars from EnSafe's Client Education Webinar Series are being hosted on our website. They're all recorded. They're all posted on our website. Usually it takes a couple weeks for them to get posted, but and once again, thank you for joining us, for tuning in today. Great job, Cody. And this concludes our presentation.
Thanks, Rich. Thanks, everybody.
Thanks, Cody.